Now that we have talked about calculating the mean temperature in the internal flows as a function of x, the next task on our hand is to calculate the heat transfer coefficient, because to calculate ultimately the rate of convection Q, we need both the rate of heat transfer, we need both the heat transfer coefficient H as well as the delta T, which requires the mean temperature Tm as a function of x. Okay. So in a circular tube, for laminar flow in a circular tube, the local Nusselt number, which ultimately will give us the value of the local heat transfer coefficient, is a constant. We already have discussed that, and it is constant throughout the fully developed region, but of course in the developing region it starts from a very high value and reduces to that fully developed fully developed region value. So for a uniform surface heat flux situation, it is again the Nusselt number based. So Nusselt number, note that the Nusselt number in this case, the Nusselt number in this case is calculated using D. Okay, so this D is the diameter of the pipe. So one has to be careful when deciding what is the length that is used for calculation of the Nusselt number. So the Nusselt number for a uniform surface heat flux situation, which is the situation where the Qs double prime value is given on the internal surface of the pipe, it is 4.36. And for the uniform surface temperature situation, that is when the surface temperature of the pipe is known, and it's uniform, it is equal to 3.66, the Nusselt number. Okay, so these values are very typical, and they are obtained using theoretical ideas. I won't go into details of the theoretical ideas, but I will give you a very brief outline. So these correlations are calculated for laminar flow situation. So we can solve the equations, the flow equations, using the by solving the flow momentum and the energy, momentum and the mass balance. And we are talking about the fully developed region. Okay, so for these fully developed region in a laminar flow in a circular tube, what we do is, let's say we have a pipe. Okay, so this let's say we have a pipe like this. These solid white lines are the walls. So we take and the flow is happening from left to right. Okay, so we take a control volume, which is an infinitesimal volume in this pipe at a radius of r, and we do an energy balance on this. Okay, so this is a zoomed in version of this control volume. So what's happening here is that since the flow is happening from left to right, so whatever heat is imparted from the pipe surface, and remember that since the flow is only in the x direction here, so the temperature, we call this temperature Tm, and the temperature on the right hand side is Tm plus an infinitesimal change in this temperature. So this is your x direction, and this is your r direction. Okay, well, let's use this as our r direction. Okay, similarly you have r defined here as well, because it's a radial coordinate. So when pipe surface imparts energy, so that flows in the radial direction as conduction. So you have the heat conducting in the r direction, because there is no convection in the r direction, because the flow is happening in the x direction. So this QR, which is the conduction in the r direction, is the heat entering because of conduction, and then the heat leaves since the volume is infinitesimal. So we call this Q at r plus dr. Okay, from the ideas of calculus, we write, instead of writing QR plus dr, we write it as QR plus dqr, which can be written as del QR by del R times dr. So this control volume height is dr and the length is dx. Okay, similarly, this temperature change, which is an infinitesimal dTm, can then be written as del Tm by del x times dx. So when you write this, then what we can say is that the amount of energy that is conducting in the r direction, which is basically this QR minus this that is leaving. So this simply becomes QR minus this thing, so it becomes minus del by del R of QR times dr. So this is the energy that is conducting into this control volume, and this is equal to the energy that is advecting from left to right because of the fluid convection. So this becomes m dot times Cp times the temperature on the right hand side minus the temperature on the left hand side, becomes del Tm by del x times dx. Okay, so starting with this energy balance, and remember this QR can be written using Fourier's law of heat conduction as minus k times 2 pi r times dx, and then you multiply that by del T by del R. Okay, so we substitute this in this equation, so that gives us a differential equation for the temperature, and which can then be solved. Sorry, I made a mistake. This is the temperature is not supposed to be Tm, it is actually supposed to be just T. Okay, because it's not the mean temperature, it is actually the local temperature, because we have taken an infinitesimal volume. So the temperature at that point is the temperature as a function of R and X both. Okay, so there is no. Okay, so when we substitute this equation number 2 in equation number 1, we will get a differential equation for temperature, which can then be solved, and then you can calculate on the surface the Nusselt number is nothing but the gradient in temperature, so that is del T, I mean the non-dimensional gradient, but you can calculate that using del T by del R at R equals R naught. Okay, so using this value, which is obtained from the temperature distribution after solving the differential equation, this can then lead us to the Nusselt number. Well, this leads us to the H, which leads us to the Nusselt number. Okay. Again, I won't, as I said, I won't solve things for you, but I'm just giving you a recipe as to how things are obtained. Okay, so going back to our previous, we'll continue with the discussion. So this all was for laminar flow, but if the flow is turbulent, then we need correlations. So let me clean this screen. Okay, so for turbulent flow in a circular tube, for if the surface of the tube is smooth, and we're talking about fully turbulent conditions, that is Reynolds number is greater than 10,000, so we are safely in the turbulent zone, we can use the Ditters-Poynter equation, which gives us the Nusselt number as a function of Reynolds and Prandtl number. It does have a coefficient which is different if the pipe's cooler than the liquid, or the fluid, or the fluid's cooler than the pipe. And then if the pipe roughness, if the pipe is not smooth, there is a certain amount of roughness in the pipe, and we are in the transition flow regime, that is Reynolds number is um, greater than 10,000, we could use another correlation, which is this one. Again, as I said, that you don't have to remember these correlations, they will be given to you. You just have to understand which one to use, which again, when you start working in the industry or you work in design as a heat analyst, heat transfer analyst, you will get that experience by using these correlations again and again. Okay. So again, not going into too much details, you will get used to using these correlations when you have to solve a problem, which we will do in a matter of minutes. Okay, so if the tubes are not circular, so as we discussed earlier, we tend to use the hydraulic diameter, which is defined as this. So we replace all the instances of diameter using this 4 AC by P as the hydraulic diameter. Okay. So again, for non-circular tubes, for laminar flow, the local Nusselt number is a constant, and you will have to refer to tables to calculate the value of these Nusselt number for non-circular tubes. Okay, similarly for turbulent flow as well. Okay. So all this discussion we have had till now is based on was based on a fully developed flow regime, but of course we have the entry region in the beginning. As we discussed earlier, that the heat transfer coefficient, or the Nusselt number, it decays and then it becomes constant. Okay, so you have this fully developed region and you have this transitional region. So in the transition region, the manner in which the Nusselt number decays depends on the nature of the thermal and velocity boundary layers. So you can see this figure where the Nusselt number, sorry, let's use a different color. So where the Nusselt number variation is given as a function of, well, just think of, see this, just see this x here. So it's given as a function of x. So we have a solid and a dotted line. So the solid line, so the dashed line, which is the thermal entry length. So this is a situation where we assume that the velocity was fully developed. It is the temperature that starts developing. But for the combined entry length case, this is a situation where what we are analyzing is that the hydrodynamic as well as the temperature boundary layers, they are both developing at the same time. Okay, so depending on how the two boundary layers are developing, whether one's already developed or not, it affects the Nusselt number variation as a function of x in the entry length region. Okay, so as I said, in the combined entry length region, the thermal and the velocity boundary layers are developing at the same time. In this thermal entry length region is where the velocity profile is assumed to be fully developed at the inlet, and only the temperature is developing. Okay. And the reason we discuss this thermal entry length situation, where we assume that the velocity boundary layer is fully developed, so we consider this for situations where the Prandtl number is very large. Okay. Remember when we talked about the fully developed length, so this was approximately this was proportional to your Prandtl number. Okay, so this was thermal entry length. So if the Prandtl number is very large, then the entry length, the thermal entry length is very large, but of course the hydrodynamic entry length is very small. So what that means is that when the temperature boundary layer is developing, you can assume that since this length is much larger than, let's say, we had the velocity development which happened here. So in most of the region, what we see is that the velocity is the green one is the velocity, so the velocity is fully developed. So we can assume that in most of this black region, in most of it the velocity is fully developed. Okay, so that is the reason we consider this thermal entry length situation. Let's clean the screen. So next is the average Nusselt number. So not the local one, but the average one for laminar flow in circular tubes with uniform surface temperature. So again, lots of correlations. So if this thing is less than 2, then the Nusselt number is simply 3.66. But if it's greater than 2, then you have to use this correlation. And the other situation is thermal entry length, that is assuming that the velocity is already developed. In that case, the Nusselt number is 3.66 plus this quantity here. The next one is average Nusselt number for turbulent flow. So in this situation, the effects of entry and surface thermal conditions are much less pronounced, so we can neglect them. So for long tubes where the length to diameter ratio is greater than 60, we can assume that the average Nusselt number is the same as the local Nusselt number. Okay, and for short tubes where this ratio is less than 60, you have to use this correlation. And then for non-circular tubes, you have again for laminar and turbulent situations, you will have to refer to the corresponding correlations. Okay, one important point. So when we are determining the average Nusselt number for any tube geometry or flow condition, all the properties, because we have to calculate thermophysical properties, so all of them should be calculated for a temperature, an average temperature of the inlet and the outlet. Because as we know that as the flow proceeds from left to right, the fluid temperature will either increase or decrease depending on if it's less than or the greater than the wall temperature. So all the fluid properties must be calculated for an average of the inlet and outlet mean temperatures. Okay. Now a question for you is, why do solutions to this such internal flow problems like in a pipe or a duct often require the use of the method of iteration? Okay, and the answer for that is because whenever you solve for internal flow problems, your Q is dependent on your H value. This is Q convection, and well, right. Q convection, and so this is H bar times A times Ts minus T mean. Okay, or well, in this case it's for the whole pipe, so this is delta T log mean. So you need to find H bar as well as delta T log mean, which contains your T outlet, right, or Tm outlet. Okay, so this if you remember, your Tm outlet requires the H bar value, and your H bar value requires the thermophysical properties which require your Tm outlet and Tm. Okay, Tm bar, which is this one. So what that means is that you have to assume, you have to start with some guess for H bar, calculate this, and then go back and then calculate H bar using these temperatures, and then you have to repeat because all the thermophysical properties for the calculation of H bar were calculated using the outlet temperature. Okay, so one has to perform a few iterations until these iterations converge. Okay, so this is the reason for such situations we often require the use of iteration, and this was not the case for external flows because there was nothing, there was no log mean temperature difference. Delta T was simply T surface minus T infinity. So T infinity was given, and T surface was also given as a boundary condition. So all we had to do was to calculate H bar using one of the correlations. But in the present situation, we need to calculate the outlet temperature, which is then used to calculate h bar, and then h bar has I mean the outlet temperature depends on h bar as well, so one has to do a couple of iterations. Okay. We also have situations where the flow happens through a concentric tube annulus, so like this. So in this situation, we have heat transfer happening through two surfaces. One is the internal surface, and one is the external surface. So internal as well as the outer surface. So one must calculate the rate of heat because the fluid that is flowing through this pipe, if it's cold, is getting hotter as it moves. So it is obtaining energy from both surfaces. So one has to calculate that. And for the internal surface, we have to use the internal pipe temperature, and for the external or the outer surface, you have to use the outer pipe surface temperature. And be careful here because don't confuse this O with the outlet temperature. So this one is the outer surface that we're talking about. Okay. Similarly, we'll have different Nusselt numbers for the internal and the outer surface of the annulus, and then we have lots of correlations to calculate this. The last topic for the discussion for this chapter is on the enhancing of internal flow heat transfer. So what that means is that if we have some situation, can we do something to enhance the amount of heat transfer that is happening between the fluid flowing and the surface of the internal surface of the pipe or the duct. So to increase the heat transfer, one way is to make the flow turbulent, because we know that making the flow turbulent increases the rate of heat transfer. So what we can do, one of the things that can be done is to machine fins into it. So when you machine different shapes into the internal surface, then that results in turbulating the flow, leading to increase in rate of heat transfer. You can also insert trip wires, which trips the boundary layer and makes it turbulent, and the flow becomes turbulent, which ultimately results in increasing the rate of increasing the heat transfer coefficient and increasing the rate of heat transfer. Now, the other thing that is done is by introducing secondary flow in pipes. So what is typically done is that since you have to give the fluid some time to flow into the pipe, so instead of having a simply straight pipe, you can have a helical pipe, something like this, like a spring, but this is a pipe in this case. Okay. So the fluid flows through this pipe, and I'm not drawn it very well, but you can, it's a helix. So when the flow, I mean ultimately the flow is going down, but it's also rotating in the process. So if I look at a cross section, then so this is a cross section like this. So although the fluid is moving down, but what we see is because of the helix, the swirl in the helix, it results in a uh, secondary flow pattern where the fluid starts to mix within the pipe. So this is the pipe cross section. So inside the pipe, as the fluid is moving down as a whole, it is also rotating, and this secondary flow ultimately creates more mixing, and increased mixing results in increasing the rate of heat transfer. Okay, but the disadvantage of these approaches is that all these approaches result in an increased pressure drop. Okay, so that adds to the cost because increased pressure drop means that you have to apply more power to allow the fluid to flow in the pipes. So now we are done with the theoretical discussion in the internal flows. We will solve a couple of problems to reinforce the understanding and how to ensuring how to use these correlations, lots of correlations that we have seen for solving real engineering problems. So let's solve example number 1, example 8.1. So for a flow of liquid metal, in this case through a circular tube, the velocity and the temperature profiles at a particular axial location are given. Okay, so the velocity profile in this case is uniform and the temperature profile in this case is parabolic. Okay, where C1 and C2 are constants. So what we have to find is the value of the Nusselt number at this axial location. Okay, so this is at some axial location where the velocity and the temperature is given to us, and this is we are talking about liquid metal, which will help us to calculate the Prandtl number if required. Okay, so let us proceed with the analysis. So remember that for Nusselt number we have to calculate the heat transfer coefficient, and the heat transfer coefficient for the external flows over circular cylinders or circular pipes is given using this relation. Okay, so Qs double prime, which is the heat flux of convecting out from the surface of the pipe. Sorry. In this case, it's internal flow. So this is the heat flux which is convecting from the internal surface of the pipe into the fluid that is flowing inside the pipe, is given as Qs double prime is H times Ts minus T mean. Okay, so in this case the T surface is known to us. Let's see if that's given to us. Okay, so the T surface is not given, but the T mean variation. In fact, in this case, the Tr minus T surface, which is the temperature at any radial location minus the surface temperature, is given as parabolic. So the first thing we have to do is we have to calculate the mean temperature. So if you remember from the definition of the mean temperature, it's given as this. So we estimate the mean temperature as the temperature that would produce the same amount of advection of the rate of heat transfer through any given cross section. So we can simply evaluate this, and as this advection integral requires the flow velocity already is given as a constant at that cross section. So when we substitute all these values, we end up getting the T mean as Ts plus C2 upon 2. So the good thing is that this relation simply gives us the value of T surface minus T mean, the difference of the temperatures. Next is for the evaluation of H in this formula, we need to calculate Qs double prime. Now since the temperature profile is given, so that is all we need to calculate the heat flux, because whatever is convecting from a surface, if you remember what we discussed earlier, that the first layer above the solid, there is convection going on. So if you have a pipe like this with the fluid flowing inside it, then if the temperature profile is the difference of the temperature between the surface and T as a function of R is parabolic. So what that means is the rate of conduction at the layer just above the solid surface is equal to the amount of heat convected overall from the surface. So this rate of heat conduction can be calculated using the Fourier's law of heat conduction. So we can simply calculate this derivative, and this helps us calculate the H value as the ratio of Qs double prime and the difference of Ts and Tm, which gives us 4k upon R0, where R0 is the radius of the pipe. Okay, and then the Nusselt number, which is based on the diameter of the pipe, which is hd by k, comes out to be 8. Again, we see that in this situation the Nusselt number is a constant. Okay. So for these such internal flows where the the boundary layers are constrained in the fully developed region, the Nusselt number becomes a constant. In this case, this is equal to 8 for the profiles which are given to us. Okay. So that solves the example number 8.1. Let's now solve example number 8.2. It talks about a more practical situation. So you have a system for heating water. So the water's inletting a pipe at a temperature of 20 degrees centigrade. Now remember, this temperature that we're talking about is the mean temperature, okay, of the water in that pipe in the inlet cross section, and the water exits at a temperature of 60 degrees centigrade. Okay, so in this heating arrangement that we have, it involves the passing of the water through a thick walled tube which has inner and outer diameters given as 20 and 40 millimeters. Okay, so it's a 10 millimeter thick tube. The outer surface is insulated, and there's an electrical heating arrangement within the wall. So this 10 millimeter wall that you have has an electrical heater embedded inside it, which produces the heat, which then gets convected to the fluid, to the water that is flowing inside the pipe. Okay. And it is also given that the Q dot, which is the energy per unit volume, the rate at per unit volume that is generated is 10 to the power of 6 or 1 megawatts per meter cube. So given the power delivered to the heater and the inlet and outlet temperatures desired for the water, these are the design conditions. We have to find out that if the water mass flow rate is 0.1 kgs per second, then how long must the tube be so that we are able to achieve a temperature increase of 40 degrees, that is from 20 degrees to 60 degrees centigrade. Again, as I said, it's a very practical situation because you have these heating arrangements where you have certain constraints. In this case, the constraint is that you want to increase the temperature of the inlet water by 40 degrees. You also have a fixed heating arrangement, so the heater is able to provide 1 megawatt per meter cube of energy, and the flow rate of the water is also constant. That's given as 0.1 kgs per second. So then the design output has to be the length of the tube. So as we increase the length, it will give more time for the water to contact the heater and extract energy out of it. So we have to find that minimum length at which we can achieve this 40-degree increase in the temperature. That's the first part. And the second part is that we have to find the local convection heat transfer coefficient at the outlet of the pipe. Now that we have found out the length, we have to find the outlet local heat transfer coefficient given the surface temperature at the outlet in the pipe. So let us proceed. Here is the schematic. So we can do a quick study of this. So we have a mass flow rate of 0.1 meters per second. You have this region in the heater. So you can see this region. So that is where the heating element, the electrical heating element is embedded, and there's insulation on the outside. So this part is insulated on the outside. So what that means is that there's no energy that can leave from the outside surface of the pipe. So whatever energy is produced by the electrical heater inside this inside the solid surface of the pipe has to be convected into the fluid. Okay, so that gives us the energy balance. So since as I just said, that whatever energy is produced by the heater or whatever power is produced by the heater has to go as the heat convected into the water from the pipe. Okay. So this energy generated by the heater is simply this Q dot, which is watts per meter cube, multiplied by the volume of the solid region of the pipe, which is the volume of the outer pipe diameter minus the internal pipe diameter. Okay. And then this has to be, so here we have assumed that we have taken L as the desired length of the pipe. Okay, so this amount of watts, which is now Q convection, has to be equal to the energy that results in the increase in the temperature of the water from the inlet temperature, which is 20 degrees centigrade, to the outlet temperature, which is 60 degrees centigrade. Okay, so when we substitute the values here, we get a desired length of 17.7 meters. That is the pipe length. So you can see how long the pipe has to be. Of course, we won't keep it in a straight section. We'll have some sort of heating arrangement like this, so that we can take less space. We can also go in the third dimension, so that we can take the minimum amount of volume to embed this pipe. Okay, let's go to the second part of the problem, which was to find the heat transfer coefficient. So if I just draw this whole pipe as a single section, then we have to find the heat transfer coefficient at the outlet of the pipe. So from again the Newton's law of cooling, the heat transfer coefficient is defined as the ratio of the surface, the heat flux, divided by the temperature of the surface, inner surface Ts, and we put an O here because it's the outlet surface temperature, because the surface temperature also may change as you go from left to right. And then you have the mean outlet temperature, which is the outlet temperature of the water. So in this case, Qs double prime is not known, but what we can do is, since the total amount of energy generated by the heater is given, which gives energy over the whole length of the pipe, we can assume that this energy is uniformly distributed, because the heating element is such that it heats all parts of the pipe uniformly. In that case, we can simply divide the total watts per meter cube by the surface area. Sorry, we can divide the total watts divided by the surface area to give us the watts per meter square. Okay. So this gives us Qs double prime, and then since we already have the temperatures with us, so the surface temperature is given as 70 degrees centigrade. So this is 70 degrees centigrade, and this temperature, the mean temperature of the water, was given as 60 degrees centigrade. So the difference is 10 degrees centigrade. So that results in a heat transfer coefficient of 1500 watts per meter square Kelvin. So you can see that it's a very large value of H that we see here. So let us solve the third example, which is the example number 8.3. Again, a very practical problem where you have to calculate the average heat transfer coefficient for a given geometry, and this is done quite a lot, because when you manufacture a pipe, or let's say you buy some heating arrangement, then you would want to calculate the heat transfer coefficient for that, for a given range of operating conditions, so that you can do some sort of optimization or control the different parameters when using those heaters. So in this case, you have steam which is condensing on the outer surface of a thin walled circular tube. Okay, so this tube, you have steam condensing on the outer surface. So what this ensures is that the outer surface temperature of the pipe is 100 degrees centigrade. Okay, this is a typical way to ensure a constant temperature condition. The diameter of the pipe is 50 millimeters, so it's not a very huge pipe in terms of diameter, and the length is 6 meters. The water flow rate is given to us. It is 0.25 kgs per second, and the inlet and outlet mean temperatures of the fluid which is flowing through this pipe is also given. So the water inlet temperature is 15 degrees centigrade, and the outlet temperature is 57 degree centigrade. So it's a good amount of increase in the temperature of the water in this pipe. So what we have to do is we have to calculate the average heat transfer coefficient associated with this water flow, so that we can then use it for further design or operating conditions control if required. So here's the schematic. To calculate the h bar, we have to simply write the Newton's law of cooling. Okay. So Newton's law of cooling states that the Q convection is h bar. So remember, we are talking about the average, so it's for the whole pipe times the total surface area. So the total internal surface area of the pipe which is contacting the liquid is nothing but the circumference, which is let's write in terms of the diameter, sorry, times the length. So that's the total internal surface area contacting the liquid, and then you have the T surface. Well, sorry, in this case we use the delta T log mean, because we're talking about the complete length of the pipe, and the temperature goes from T mean inlet of 15 degrees to T mean outlet of 57 degrees centigrade, and the surface temperature is 100 degrees centigrade. So to define a delta T in this case, we use the log mean temperature difference, as we saw in this lecture earlier. So we simply have to use this formula to calculate h bar. Now a Q convection is not known to us, but we know that the water flow rate is given to us, and the water temperature increase is also given to us. So we know that Q convection is whatever heat is convecting from the pipe inner surface to the liquid is ultimately going to increase the liquid temperature. So this is from energy balance, we can write this as m dot Cp, and then T mean outlet minus T mean inlet. So this equation number 2 can be used to calculate Q convection, and which can be substituted into equation number 1 to then calculate the h bar, because everything else is given to us. So this is exactly what is done here. So this is obtained by substituting 2 in 1 this way, and then since you need the log mean temperature difference here, you can calculate this using the LMTD formula, and this gives us a log mean temperature difference of 61.6 degree centigrade. So when you substitute these numbers, you get an h bar of 755 watts per meter square Kelvin. Now you can see that this is again a very high value of h bar if you compare it to the forced convection h values earlier, which were typically much modest, of around 50 or 100. So now we have started to see much larger values of h bar for these heating arrangements. Let us solve one more example, example 8.6. Again, a very practical situation. So you have hot air which is flowing through an uninsulated sheet metal duct. Okay, so in these residential buildings, you tend to have these sheet metal ducts made up of thin sheet metal. The air is flowing at a mass flow rate of 0.05 kgs per second. Okay, and the diameter of the duct is given, which is 0.15 meters, and you have the hot air entering at 103 degrees centigrade, and after a length of 5 meters, which is the length of the duct, it cools to 85 degrees centigrade. The heat transfer coefficient between the duct outer surface and the ambient air is given as 6 watts per meter square Kelvin. So let's say that you have the circular duct. So hot air is flowing from the inside, but as the hot air flows, its temperature changes. So the only way the temperature can change if the energy is convecting out from the surface of the duct. Okay, so T infinity is given as 0 degree centigrade, so it's extremely cold outside, and the corresponding heat transfer coefficient is given as 6 watts per meter square Kelvin. That's again on the outside surface of the duct. So what we have to calculate is the amount of heat loss first from the duct for this whole length L, and then we have to determine the heat flux, which is Q S double prime at x equal to L. So that is at the outlet of the duct. We have to figure out what is the amount of heat flux that is leaving the surface of the duct, and we also have to find the duct surface temperature. So we have to calculate both Qs and Ts at the outlet. Okay, so let us proceed. We have the schematic again here, but I already have drawn it. The first part is quite straightforward. We simply have to do an energy balance. So the air enters at 103 degrees centigrade as shown here and leaves at 85 degrees centigrade. So this 18-degree drop in temperature is the amount of heat that is leaving. So you have the mass flow rate given to you. The specific heat has to be found out from tables. Now remember that the temperature of the air is changing. So you calculate the specific heat, which is calculated here, at an average mean temperature. So that means that you have the inlet temperature and the outlet. So this T mean average is the average of the inlet. Well, let's call it the mean temperature at the inlet and the mean temperature of the outlet. So be careful when doing these calculations. So we calculate Cp at this temperature and then the outlet minus the inlet temperature, which gives you, well, we have to find the loss. So this is a loss is 910 watts. So that's the amount of energy that is leaving the surface of the duct. Now the second part requires us to calculate the surface temperature at the outlet, which is the temperature here, and the heat flux at the outlet as well. So for that we have to draw the circuit. So what's happening at the outlet is that there is some temperature on the inside, there is some temperature on the surface, and there is some temperature on the outside. So the outside temperature is T infinity. The surface temperature has to be found out, and the inside temperature is T mean outlet. And we have the corresponding resistances. Now remember that the thermal resistance is defined in such a way so that the delta T is equal to the rate of heat flow times the thermal resistance. So in this case, we are interested in the flux, so we divide that by the area. So then we have to multiply by the area as well. So what we do is, instead of writing R thermal, we write R thermal times the area. Okay. So and instead of writing the heat current as watts, we write watts per meter square. So we write the current flowing as Qs double prime. This L denotes the Qs double prime at the outlet, so that at x equal to L. Okay, and then the inside temperature is Tm comma L, and then you have the resistance because of convection from the inside fluid, which is 1 upon HA, but since you are now writing the resistance times the area, so this simply becomes 1 upon H, and this L in the bracket denotes the local heat transfer coefficient at the exit of the pipe, so that is at x equal to L. Okay. And then you have the pipe surface, which is the temperature T surface at x equal to L, and then you have a resistance because of convection to the outside air, which is 1 upon HO, and then you have the outside temperature, the ambient, which is T infinity, which is 0 degree centigrade. Okay, so we can simply write the total potential drop as the inside temperature minus the outside temperature, and we can calculate the total resistance as a sum of these two resistances in series, which gives us the expression for the Qs double prime. Now remember that H out is given to us. It's already given to us in the problem. I think it was equal to 6 watts per meter square Kelvin. But H at the outlet of the pipe is not known. So now we have to use the correlations to find this H at the outlet, the local heat transfer coefficient. So for that we have to figure out whether the flow is laminar or turbulent inside the pipe. Okay, so for that we have to check the Reynolds number. So we calculate the Reynolds number based on the diameter of the pipe, and this comes out to be around 20,000. And we know that if the Reynolds number is greater than 10,000, then we are safely in the turbulent regime. So the flow is turbulent, and then now we have to check whether we are in the developing region or the fully developed region. Okay, so when you calculate the length of the pipe upon the diameter ratio, you get 33.3. And now we also saw that if the L by D ratio is the L by D ratio is typically 10 for turbulent flows for the size of the entrance length or the developing region. So we see that it is much more than 10. So we are safely in the fully developed region. So the flow is turbulent and it's fully developed. So we can then use the correlation we talked about in equation 8.60, which was the Dittus-Boelter correlation. I can actually show that to you. Yeah, so here's the Dittus-Boelter equation. So this gives us the Nusselt number for a fully developed flow in a turbulent for smooth circular tubes. Okay, so what we need is so this also has a parameter n, where the value of n is equal to 0.3 for cooling. So in this case, we are the air is cooling as it goes from left to right. So that means the surface temperature is less than the temperature of the fluid. So we have to use n equal to 0.3. So let's go back to the problem. So we use this correlation to calculate the Nusselt number. Nusselt number is the local Nusselt number here, which is the heat transfer coefficient, the local one, times D upon the K. Okay, so if we put n equal to 0.3 as you see here, so that gives us the Nusselt number of as 56.4. Again, you can see that it is a constant, but it is neither equal to the value for constant heat flux or neither equal to the value for constant surface temperature. So this is a situation where neither Qs double prime is constant or nor T surface is constant. Okay, so from this we can calculate the local heat transfer coefficient, which is 11.5 watts per meter square Kelvin. Okay, so not very large, which is good because we not very large because we're talking about the exit situation of the pipe. Well, it's actually supposed to stay constant throughout the pipe. Okay, but it's not a very large value, which is kind of good for us because we don't really want to lose the heat. Okay, so this duct is not supposed this duct is not used for heat exchange. It is simply used for transporting this hot fluid. That is the reason you see that this value is not very large. And you can insulate the duct further if you want to reduce this value. If you insulate the duct, you will end up reducing this value. Okay. So given the H value now, so you can calculate the Qs double prime because you now have the value of the local heat transfer coefficient. You also have the outside heat transfer coefficient. You have the temperature drop. So that gives you the heat flux, which is 335 watts per meter square. Now the next thing was to calculate the surface temperature. So for that, what you do is in this circuit, since the Qs double prime is not now known to you, so you need to calculate this temperature. So you can take this part of the circuit and you can simply say that the potential drop T mean minus T surface is equal to the rate of heat transfer, the heat flux, which is now known, times the resistance, which is also known from the Dittus-Boelter equation. So when you do that, it gives you the surface temperature as 55.9 degree centigrade. A couple of things to be careful about. One is that remember, it's extremely confusing for many people that what temperature has to be used for calculating your thermophysical properties. So in the first part where we had to calculate the rate of heat loss, we used the specific heat which was calculated at the average of the inlet and outlet temperatures of the air. So be careful with that.